This story is about a limit, about the point where instruments end and thought alone begins. Not about a new planet and not about a new galaxy, but about what lies beyond, a space where no signal, no light, no gaze will ever reach. I will tell you about a place that exists and is forever closed to verification, about how science works where observation is impossible, and about how that work still makes sense, though of a completely different kind than what we are accustomed to expecting from knowledge. What is at stake here is not a discovery, but the very boundary of knowledge itself. Within the visible sphere, approximately 46 billion light-years in radius, is gathered everything we will ever measure. Stars, galaxies, atoms, observers, the relic glow of the dawn of time. Everything else lies beyond the horizon. And this horizon is not the limit of a telescope, but a property of space itself. It expands faster than light can travel. This means that a vast portion of the universe, possibly thousands or millions of times larger than the visible, is separated from us not by distance, but by the very nature of expansion. No signal will ever reach it. Not a single photon will return from it. What exactly is there, we can only calculate. Supervoids spanning several billion light-years, regions with different physical constants, closed geometry through which light travels forever in circles, domain walls, cosmic strings, pockets of inflation with their own laws. Each of these possibilities does not contradict the equations, and none can be confirmed. The longer we look within the bounds of the observable, the clearer it becomes how small our accessible portion is, and how deep the silence beyond its edge. And as you gaze at the night sky, do you ever think about the fact that most of the universe will never appear before any observer? What matters more, knowing the answer, or learning to live with a question that will never have one? And how do you feel about knowledge that cannot be verified by direct measurement, but follows logically from everything already verified? Listen, this story is about that. What draws a person toward a space where nothing familiar exists? No warmth, no footing, no answer. Perhaps that is precisely where something important about ourselves is hidden. Deep space is not merely a direction on a star chart. It is a cold, nearly empty, and infinite expanse that draws the mind with inexplicable force. A mind ready to venture beyond the familiar. Behind this attraction lies something greater than curiosity, a drive to understand where all that exists came from, how the fabric of reality is structured, and where we stand within that fabric. The mind responds to cosmic uncertainty in a particular way, not with fear, but with something closer to concentration. Familiar reference points disappear. Reliable supports fall away. But in their place comes a rare opportunity to see reality at its true scale. This special mode of perception allows one to simultaneously grow calm and sink into reflection. Much as a night lecture about distant regions of the universe opens a path into hypotheses and measurements where human imagination touches the limit of the possible. Distant regions of space are not merely remote points on a map. They are immense structures that expand along with space itself. And this space, for all its apparent emptiness, is not empty in the full sense of the word. It is filled with energy, quantum fluctuations, and faint radiation that has traveled to us from the deepest of epochs. Modern observations show that on scales exceeding many billions of light-years, the universe appears relatively uniform. But behind this outward calm lies a complex and dynamic fabric, threaded through with gravity, dark matter, and streams of radiation moving through space over inconceivably long stretches of time. A telescope points at the sky, but sees the past. The farther the object, the older its light. We observe moments stretched across billions of years, and in this lies the first great paradox of astronomy. Light is the only carrier of information from the depths of space, but its finite speed makes every image in the telescope a picture of a long-gone era. Every galaxy, every stream of radiation reaching our instruments, this is not what exists now. It is what existed once, sometimes billions of years ago. There is an almost philosophical dimension hidden here. We never observe the universe as it is in the present moment. We gather scattered fragments that propagated toward us over vast spans of time and try to assemble from them a coherent image. By current estimates, the radius of the observable universe is approximately 46 billion light-years, and this figure seems paradoxical when one recalls that the universe itself is about 13.5 billion years old. How can its visible portion be larger than the distance light has managed to travel in all that time? The explanation lies in the expansion of space. Light began its journey in an era when distances were incomparably smaller, and then space itself continued to stretch, extending the paths of photons. This phenomenon shows that deep space can hide regions we will never see. Their light simply will not make it to us, no matter how long we wait. But if we see only the past, what hides in the place where light will never arrive? The universe is not chaos. It is a gigantic, three-dimensional web of invisible matter, and part of this web extends beyond the horizon, from which light will never return. According to modern models, the distribution of galaxies forms a network resembling a volumetric cosmic web. The threads of this network consist of dark matter, a substance that interacts gravitationally but does not participate in the familiar electromagnetic interactions. These threads form the scaffolding around which galaxies cluster. Viewed from sufficient distance, such structures resemble neural networks or biological systems, only magnified many times over to scales that have no analog in anything terrestrial. If one mentally moves toward ever more distant regions, an interesting effect emerges. The rate at which objects recede grows to such a degree that some of them pass beyond the observability horizon. This is not a physical movement of galaxies through space. It is the expansion of space itself. As a result, there exist regions from which light will never arrive. The distance between them and us increases faster than any radiation can propagate. Such regions are called the cosmic horizon, the limit beyond which a portion of the universe lies hidden from all instruments and all technologies. Even within the visible horizon, there are processes that remain poorly understood. Gigantic voids, spaces hundreds of millions of light-years across, nearly devoid of galaxies, are still explained only in the most general terms. Some models treat them as an inevitable result of large-scale structure formation. Others admit a connection to effects that have not yet received a rigorous theoretical explanation. Meanwhile, the very fact of the existence of such voids indicates that the universe is organized not uniformly, but as a complex pattern. And beyond the horizon, that pattern may be entirely different. But before we venture into the unknowable, what happened at the very beginning when observation was altogether impossible? The first 400,000 years were absolute darkness for any telescope. During this period, the temperature of the universe was so high that atoms could not exist in stable form. Space was filled with a hot plasma of free electrons and photons, which collided and scattered, preventing light from propagating freely. Only after the universe had cooled sufficiently and electrons combined with nuclei to form the first atoms did space become transparent to radiation. Everything that happened before this epoch of recombination is forever hidden from direct observation. No one will ever see what occurred there. Only equations can lift the veil, and even then, only indirectly. It was in those first moments that all structures were seeded, both those we see and those forever hidden beyond the horizon. Now a key question arises. What if beyond the horizon lies an exact copy of our universe, or a region where physics operates by entirely different rules, and that, there, is the norm? Modern theories allow both scenarios. The first assumes global uniformity. Regions beyond the horizon resemble our own zone and contain analogous structures, galaxies, filaments, voids. This scenario is consistent with inflationary models, which prescribe strong leveling of initial fluctuations and make the universe resemble itself in every direction. The second scenario allows for variations in physical parameters. In that case, the properties of matter, energy density, and even the basic physical constants may differ in different regions. For example, some hypotheses posit the existence of regions with different values of physical constants, different densities of dark energy, or even different geometries of spacetime. These ideas are discussed within inflationary cosmology, which allows that different parts of the universe may have formed under different conditions. The radius of the visible portion of the cosmos is approximately 46 billion light-years. But this is only a small fraction of the full structure, and theoretical estimates allow that the total size of the universe exceeds the observable region by hundreds, thousands, or even vastly larger multiples. Both scenarios are consistent with current theories, but neither is susceptible to direct verification. An answer might come from a single source, an ancient glow permeating all of space since the dawn of time. In the tiniest fluctuations of this ancient glow may lurk traces of structures we will never see directly. The cosmic microwave background, a relic of the epoch of recombination, is one of the most powerful sources of information about the early universe. Observations of this background show small temperature fluctuations reflecting the primordial inhomogeneities. They are distributed almost uniformly, testifying to a high degree of symmetry at the beginning of time. However, these observations also contain small anomalies difficult to explain solely through internal processes. Some researchers connect them with the possible influence of superscale structures located beyond the horizon. This is the only thread to the invisible, and its interpretation remains the subject of debate. Causal isolation is not a technical limit of our instruments. The accelerated expansion of space creates a boundary beyond which neither light nor any signal will ever arrive. Because of this acceleration, there exists a threshold beyond which a source of radiation recedes faster than light can travel, and information about these regions remains forever inaccessible. The visible universe is only a part of a more extensive structure, and an observer will never receive direct data about what happens beyond the horizon. But where did the primordial inhomogeneities come from? The answer lies in the very first moment. A random quantum tremor in the first seconds of the universe's existence determined where galaxies would later arise, and where eternal emptiness, spanning billions of light-years, would remain. The quantum fluctuations of the first moments were stretched by inflation to gigantic scales and became the seeds of all the visible structure of the cosmos. Where the amplitude of these fluctuations was higher, more massive formations could take shape, now hidden beyond the horizon and inaccessible to observation. It was from these initial perturbations that the filaments, nodes, and voids we observe today inside the visible sphere grew. One consequence of these early processes is cosmic domains, regions arising from phase transitions in early cosmic fields. During such transitions, the field could take different values in different regions of space, creating a mosaic of domains with unique parameters. If this occurred, then beyond the horizon, there may exist regions with different values of the fundamental constants, regions where structures formed without analogs in the known galactic systems. In some variants of these models, uneven inflation created regions with substantially different expansion dynamics. Some expanded faster, others more slowly, forming a complex mosaic that still exists somewhere there, beyond the limits of our horizon. But what specifically could dark matter and dark energy have created in these invisible regions? What if beyond the horizon there exists a region spanning several billion light-years where there are almost no galaxies at all, only darkness? Or conversely, an unimaginable concentration of structures that has nothing to compare to. Dark matter forms gravitational scaffolding on which ordinary matter gathers. If its distribution beyond the horizon differs from what we observe, this could lead to the formation of structures that have no analogs in the visible portion of the cosmos. Theoretically possible are massive halos of dark matter containing virtually no baryonic matter, enormous gravitational constructions without a single star. Their existence is difficult to verify, but physical models do not exclude their emergence under conditions where density fluctuations had higher values. Dark energy, making up the larger part of the energy structure of the known cosmos, drives the accelerated expansion of space. Its density is distributed across all of space almost uniformly. However, modern models allow for small variations at super-large scales. If such variations exist, then in distant regions there may occur processes not observed in nearby regions. In some zones, the acceleration of expansion may be higher, in others lower, creating a complex dynamic picture. There could exist peculiar pockets where galaxies recede from one another considerably faster than in the known regions. Quasars in the early universe testify that supermassive black holes with masses of millions or billions of solar masses formed very quickly. If similar processes occurred in distant regions, there may exist there zones with elevated concentrations of black holes, creating strong gravitational fields. Such regions could be entirely invisible because of their remoteness, yet exert an influence on the overall structure of space. Supervoids beyond the horizon could span several billion light-years across, regions where gravitational dynamics differs radically from the familiar, and light passing through them experiences no appreciable gravitational effect. Beyond matter and energy, the early universe could have left behind traces of a far more exotic nature. Strings, walls, traces of phase transitions that divided space into domains, forever hidden, never to be discovered directly. Cosmic strings are one-dimensional objects with colossal energy density that could have arisen in the early epochs during symmetry-breaking transitions in cosmic fields. These structures are capable of forming complex patterns and influencing the distribution of matter on large scales. If beyond the horizon lie regions where such strings form large nodes, their influence on the dynamics of space could be quite significant, although no direct evidence of their existence has yet been found. Domain walls, two-dimensional boundaries between regions of space in different quantum states, represent another class of relic structures. They can attain significant dimensions and extend far beyond the observable universe, creating effects associated with changes in the distribution of light and matter. Their influence may manifest as faint anomalies in the distribution of radiation or as large-scale structures, but we have no direct evidence of their existence. The multiverse hypothesis considers the possibility that uneven inflation created many isolated pockets, bubbles of space, each of which is an independent region with its own physical parameters. If this model is correct, then the distant zones of our cosmos may be not merely boundaries, but transitions to fundamentally different regions of reality. Verifying this idea is impossible, since the boundaries between such domains are fundamentally inaccessible to observation. They may exist, and we will never know it. And if physical parameters can vary from region to region, then the very geometry of space beyond the horizon may be fundamentally different. Space can be curved, closed, possessing a shape impossible to imagine in familiar categories. There, beyond the horizon, light may travel in closed paths forever, and no one will ever know. Within the framework of general relativity, the geometry of space is determined by the distribution of matter and energy. If in distant regions these parameters differ from the average, the geometry may be fundamentally different. Space may have positive curvature, in which case it resembles a closed, multidimensional sphere, inside which light can propagate along complex trajectories and structures stabilize locally. Space may have negative curvature, and then hyperbolic configurations arise, forming different types of gravitational objects. Modern research also allows for the possibility of a multiply-connected topology of space. It may be not simply infinite, but possessed of properties that are difficult to intuit, closed trajectories along which radiation circulates endlessly, or transitional regions between zones of different geometry. If such topology exists on scales exceeding the observable region, then beyond the horizon there may lie regions where space connects back to itself. Observing such features is impossible, but their existence does not contradict any current theory. All of this leads to the central question: where does the absolute boundary of human knowledge lie? It is not that telescopes are weak. Space itself forbids any connection with these regions. The causal horizon is not a technical limitation of instruments, but a fundamental property of spacetime. Neither light nor gravitational waves, nor any other information carriers will arrive from there. This is a consequence of equations, not a deficiency of technology. This is precisely why understanding deep space requires the joining of physics, mathematics, and philosophy. Observation ends where calculation begins. There may exist regions with different physical constants. For example, with different values of the fine structure constant or different masses of elementary particles. Such variations could lead to the formation of structures unlike anything known. The possible existence of regions with additional spatial dimensions is also considered. In some theories, space has more than 3 dimensions, and these extra dimensions may be hidden under ordinary conditions, but manifest as anomalies in distant regions. In regions with substantially different energy density, time could flow at a different rate, and this is not science fiction, but a logical consequence of the equations of general relativity. And yet we have a single instrument that reaches beyond this boundary. That instrument is theory. Physical models are applied not only where data exists, but also where data does not and cannot exist. The nature of deep space becomes the object not of direct observation, but of the logical extension of known laws. Using the theory of gravitation, inflationary cosmology, data on the distribution of galaxies, and the cosmic microwave background, researchers construct pictures of processes unfolding at super large scales. These pictures may differ from one another, but they are grounded in calculations verifiable within the observable region. This extension of models beyond the horizon makes it possible to imagine the structure of the cosmos there, where it is hidden from all telescopes. Matter is not distributed uniformly. It forms nodes, filaments, and voids. If one regards the large-scale structure as the product of early fluctuations, then there must exist a certain distributional principle that governs the universe as a whole. These fluctuations arose from quantum tremors stretched by inflation across vast distances. Consequently, if this model is followed, structures analogous to those visible inside must exist beyond the observational horizon. They may be larger, denser, or more extended, but the general principle of their formation should remain the same. At the same time, certain scenarios posit variations in the amplitude of initial fluctuations in different regions, meaning that beyond the horizon, there may exist regions with fundamentally different structure, either with exceptionally high concentrations of matter or with almost none at all. Dark matter forms the gravitational scaffolding on which ordinary matter gathers. If its distribution beyond the horizon differs from what we observe, this could lead to the formation of structures without analogs in the visible portion. For instance, giant halos containing almost no baryonic matter. Such structures would dominate the dynamics of space, leaving no luminous traces. Physical models do not exclude them, but their existence cannot be verified. The radiation density level in the most distant regions may also have evolved differently from regions from which light will someday reach us. If in such areas there were processes differing from the known ones, the radiation level could have had deviations that remain forever beyond the horizon and cannot be measured. Gravitational waves of primordial origin arising during inflationary field oscillations may have wavelengths exceeding the size of the observable universe, and then they would exist beyond the horizon, leaving no direct traces. One of the key hypotheses remains the idea of supervoids, regions almost entirely devoid of matter. In the observable universe, such voids span hundreds of millions of light-years. If this model is scaled up, then beyond the horizon there may exist even more extensive voids, reaching several billion light-years across. They could represent regions where gravitational dynamics differs radically from the familiar, and light passing through them experiences almost no gravitational effect. Their opposite could be superdense clusters, regions where density fluctuations in the early epochs had a large enough amplitude to lead to the formation of structures that exert a significant effect on global dynamics. In some variants of theoretical models, the possible existence of regions with different geometry of space is considered. Space may be positively or negatively curved. In regions with positive curvature, there may arise effects leading to the local stabilization of structures. In regions with negative curvature, different configurations of gravitational objects may form. Such features could be products of early epochs, when energy density was exceptionally high and quantum fluctuations had enormous amplitude. Relic structures, domain walls, and cosmic strings may also pass through regions beyond the horizon, creating anomalies in the distribution of radiation or influencing the shape of large structures. The existence of regions with different expansion dynamics, variations in vacuum energy density, multiply connected topology, regions with high concentrations of primordial black holes, zones where stars could not form because of excessively low matter density, or conversely, where they arose far more quickly and were more massive. All of this is considered by theoretical models as possible, logically self-consistent scenarios. Thus, beyond the observational horizon, there may lie a great diversity of structures and states, large concentrations of matter and gigantic voids, variations of dark energy, quantum boundaries, inhomogeneities of early epochs, relic formations, and regions with different values of physical parameters. The radius of the observable portion of the cosmos is about 46 billion light-years, and this is only a small fraction of what exists. Understanding the hidden regions requires the combination of theoretical analysis, mathematical models, and indirect observations, compelling researchers to posit the existence of complex processes in places where light will never reach an observer. Deep space exists, evolves, forms structures, and remains forever hidden. And it is precisely this that makes it the most powerful platform for hypotheses. A space where calculation becomes the only compass in the absolute darkness of the invisible. The distribution of matter beyond the horizon is determined not only by quantity, but by the character of the dark matter structure itself as it permeates the hidden regions. Within the observable cosmos, dark matter is organized in a recognizable pattern: extended filaments, nodal points at their intersections, and vast voids between them. This scaffold arises as the natural consequence of gravitational dynamics launched by primordial density fluctuations. But if in distant regions the initial fluctuations had a different amplitude or a different spatial distribution, then the very character of the forming scaffold could have differed fundamentally. Instead of compact filaments, diffuse clouds. Instead of sharp nodal clusters, dispersed plateaus with a gradual increase in density. Under such conditions, galaxies might have arisen considerably more slowly, their clusters would have been less compact, and the overall architecture of space would have unfolded by an entirely different scheme. Regions with elevated concentrations of dark matter would produce the opposite effect. The gravitational potential wells in such regions are so deep that baryonic matter gathers in them at high speed, generating dense clusters of hundreds of thousands of galaxies where the observable portion counts mere dozens. Such superstructures could have taken shape already in the early epochs, when the expansion of space had not yet reached its current rate, and have since been growing, increasing not only in mass but in extent, capturing ever new volumes of space. Their light crossed the horizon long before any observation became possible, but their gravitational imprint, a barely perceptible anisotropy in the distribution of cosmic background photons, may partly persist within the visible sphere as a faint, nearly indistinguishable anomaly. The opposite extreme is represented by regions where the concentration of both dark and baryonic matter was initially negligibly small. In such areas, gravitational dynamics did not manage to trigger the formation of even the rudiments of structures. Clouds of neutral hydrogen, failing to reach the threshold of gravitational collapse, continued to disperse, giving rise to neither protogalaxies nor stellar clusters. Over time, such regions would have turned into supervoids spanning several billion light-years, spaces devoid not only of galaxies, but of the very filaments of dark matter that under normal conditions permeate even the emptiest regions of the visible cosmos. In such zones, the gravitational potential is practically zero, and light passing through them undergoes no appreciable distortion. To an outside observer, this would be absolute, untouched emptiness. Dark energy intensifies this contrast. If its density in certain regions exceeds the average value, the acceleration of expansion there grows at a faster pace. Space between objects increases more quickly. The bonds between structures weaken before they have the chance to consolidate. Ultimately, such regions become isolated, not because something prevents entry from outside, but because expansion itself creates an insurmountable distance. These peculiar islands of space-time evolve on their own, subject to the same physics but with different initial parameters, and their history remains forever beyond the reach of any knowledge. Beyond variations in the distribution of matter and energy, the early universe could have left, in the hidden regions, traces of a far more exotic nature. Structures that arose not from the gradual gravitational growth, but from sharp, nearly instantaneous changes in the state of cosmic fields. Among such structures, cosmic strings occupy a special place. One-dimensional topological defects that arose during symmetry-breaking transitions in the early fields. They resemble nothing in the usual sense. They are not threads of matter and not streams of radiation, but autonomous objects of spacetime with colossal tension and enormous energy density concentrated in an infinitesimally thin, one-dimensional object. Wherever such a string passes, it slightly curves the surrounding space, creating the characteristic effect of a double image for everything behind it. If beyond the horizon there exist strings stretched over distances exceeding the size of the entire observable sphere, their gravitational effect could manifest in the visible portion as faint, nearly imperceptible anomalies in the distribution of the cosmic microwave background. Detecting them is extremely difficult because the effect is small, but the theoretical possibility of such detection is not excluded. Domain walls, two-dimensional analogs of strings, form during phase transitions when fields in different regions of space settle into different minima of their potential. If during and immediately after inflation, different parts of space found themselves in different quantum states, then at the boundaries between them there would have arisen planar structures with high energy density. These walls separate regions not merely spatially, but physically. On different sides of such a wall, the fields may have different values, which means that the fundamental parameters of physics, particle masses, coupling constants, may differ. Beyond the horizon, there may exist regions bounded by such walls, regions inside which the laws of physics operate differently, though within the same general logic of the equations. The idea of the multiverse grows from these concepts naturally. If inflation occurred unevenly, and chaotic inflation points precisely to this, then different regions of space could have gone through inflationary expansion with different parameters. Each such region became a kind of pocket, an independent region with its own set of initial conditions, and possibly its own values of the physical constants. In such a picture, our observable region is only one of a countless multitude of such pockets, separated either by domain walls or simply by a distance that is insurmountable because of accelerated expansion. These pockets do not interact with each other in any observable way. They are forever isolated, yet their existence follows from the same equations that successfully describe our portion of the cosmos. If physical parameters can differ from region to region, then the geometry of space itself beyond the horizon may be fundamentally different. The geometry of spacetime is determined by its energy content. This is not a metaphor, but a direct consequence of the equations of general relativity. Where energy density exceeds the critical value, space acquires positive curvature. Where it falls below the critical, negative. Where they coincide, space remains flat. Within the observable sphere, curvature is extremely small and close to zero. But beyond the horizon, where initial conditions could have differed, curvature could have taken different values and could retain them to this day, determining the entire subsequent history of those regions. A region with positive curvature resembles the three-dimensional surface of a multidimensional sphere. Space is closed in on itself, finite in volume and yet without edges. In such a region, a ray of light moving in a straight line would eventually return to its starting point, having encircled the entire closed space. Large structures in such a region would form differently. Their dynamics would be determined not only by the local distribution of matter, but by the aggregate properties of the entire closed volume. Moreover, such a region, under certain conditions, could begin to contract, a reverse motion that in our expanding universe is not observed, but which the equations admit as one of the realizable scenarios. A region with negative curvature, hyperbolic space, represents the other extreme. It expands faster than flat space, and structures within it develop according to different laws. Gravity weakens with distance more strongly there than under familiar conditions, and the probability of forming bound systems is reduced. Such a region could give rise to galaxies of a different type, more diffuse, with a smaller share of dense central nuclei and less pronounced spiral structure. If beyond the horizon there exist extensive zones with hyperbolic geometry, then the history of stars and galaxies there unfolded by a different scenario from the very beginning, and that different future remains forever beyond any observation. Multiply connected topology adds yet another level of complexity. Space may be not simply curved, but organized in a non-trivial way. Different parts of it are connected such that a straight-line path through such space eventually closes. In such a space, there arise closed trajectories along which a ray of light returns to its starting point from several directions, creating not one but multiple images of the same source. If such topology is realized in regions beyond the horizon, then light once emitted from there continues to circulate along closed paths, not reaching the observer and carrying no information to him. For those regions themselves, this would mean unique conditions for the propagation of radiation and heat, which would affect the rate of evolution of all internal structures. All of this leads to a question that transcends any specific hypothesis about dark matter, curvature, or strings. Where exactly does the absolute boundary of knowledge lie? And what does this mean for science as such? The causal horizon is not a technical limitation of instruments and not a consequence of insufficient research funding. It is a fundamental property of spacetime, following directly from the finite speed of light and the dynamics of accelerated expansion. Neither an object, nor a process, nor a signal from beyond this boundary can reach the observer. Not because some obstacle stands in the way, but because the space between them increases faster than any information can traverse it. This is not a barrier that can be circumvented with some hypothetical future technology. It is a boundary built into the very structure of reality and acting equally for all, regardless of the position of the observer. Beyond this boundary, there may exist regions where the physical constants have different values. The fine structure constant, which determines the strength of electromagnetic interaction, could have taken a different number in those regions. The masses of elementary particles, which set the nature of chemical bonds and the structure of atoms, could have been different. These are not merely abstract numbers. Literally everything depends on them. Whether stars burn, whether stable atoms exist, whether complex multi-level structures of matter are possible. In a region with different constants, stars might not ignite at all, or burn 4 times as brightly and exhaust their fuel in thousands of years instead of billions. There could exist matter in forms not provided for by known physics, and structures that have no analogs in the familiar equations. Additional spatial dimensions, an idea predicted by a number of theories, including string theory and multidimensional models of gravity, in the observable region remain hidden or manifest extremely weakly. However, under conditions of different energy density and different initial states of the fields, these dimensions could unfold, becoming accessible to the dynamics of matter. If such conditions were realized in the hidden regions, then there could exist there structures fundamentally indescribable in the framework of three-dimensional space. Objects interacting through extra dimensions and organized according to laws that in three-dimensional projection would appear as inexplicable anomalies. Finally, time. The rate of its flow depends on energy density. Where it is higher, time slows. This is a direct consequence of general relativity, confirmed experimentally many times over. In regions with substantially different vacuum energy density, the difference could be not negligibly small, but significant. 1 billion years in such a region would correspond to a different number of billions of years in the observable portion, and the evolution of structures would proceed at a different rate. If such a region arose simultaneously with ours, its current state would correspond to a fundamentally different stage of development. And what is happening there now has no direct analog in the observable universe. Nonetheless, physics possesses an instrument that acts where no telescope penetrates and no signal arrives. That instrument is theory, applied to regions where there are and never will be direct data. Equations verified against the observable portion of the universe retain their logic at any point in spacetime, provided none of the fundamental assumptions is violated. Extrapolating these equations beyond the horizon is not an arbitrary act and not a scientific fantasy, but a forced and logically justified step. There are simply no other instruments. Accepting this condition, a researcher gains the ability to describe regions that will never be observed, not with certainty that things are exactly so, but with certainty that within the framework of known physics, things could be exactly so. This is a special kind of knowledge, not measured, but calculated. Variations in the initial density fluctuations, stretched by inflation to scales exceeding the observational horizon, set the original differences between regions. Where a fluctuation was large, there a structure formed. Where small, there emptiness remained. These differences may exist on scales incomparably larger than 46 billion light-years, the radius of that portion of the cosmos accessible to any observational method. The full universe, according to certain models, exceeds the observable sphere by many orders of magnitude, possibly an infinite number of orders. The observable portion in that case is a random local patch, carrying within it only one of the realizations of initial conditions, the one that led to the emergence of stars, galaxies, atoms, and observers. The recognition of this contingency is one of the most profound consequences of modern cosmology. The hidden regions never answer. Their light will never reach us. But it is precisely in this absolute inaccessibility that a particular scientific value is concentrated. It demands the creation of theories that describe not only what can be seen, but what is in principle inaccessible to observation. A theory that withstands this limit and remains internally consistent where the data runs out becomes truly fundamental. The radius of the observable universe is approximately 46 billion light-years, and in this space is concentrated everything we will ever be able to measure, weigh, and verify. Everything else exists in the form of hypotheses, equations, and conjectures, an infinite space of theoretical thought in which invisible regions unfold as the mathematics permits. This boundary between the measured and the calculated does not limit science. It defines its deepest and most honest direction. Please write in the comments how this lecture struck you. It genuinely matters to me whether it resonated with you. Do you think science makes sense where direct observation is fundamentally impossible? Yes or no? And one more thing, do you prefer horizontal video or vertical for a phone?